So this is CPM Calculus, Chapter 2, number 50. So here we're given two functions. F of x is log of 3 minus x, and g of x is equal to the square root of x minus 3, quantity, minus 2. So first, part A, we're asked, what is the domain of each function? So remember, let's look at f of x first. So f of x is equal to log 3 minus x. Now we know whenever we have a log function, the input always has to be greater than 0. Okay? So no matter what the input is, this thing, 3 minus x, has to be greater than 0. That's the only constraint on our domain. This input has to be greater than 0. So now all we do is just solve for x. So minus 3, negative x is greater than negative 3. Divide by negative 1. X, remember to change the sign whenever we divide by negative or multiply by negative, is less than 3. So our domain for f of x, so f of x domain is equal to what? X is less than 3, from negative infinity to 3, use a parentheses because we don't include the 3. This is our interval notation right here. Okay, this right here is inequality notation, so domain can be seen in different ways. Okay, you can even use a number line, and then this is 3, open circle, and we're shading to the left. Okay, anyway, let's look at let's look at the next part, g of x. G of x is equal to square root of x minus 3 minus 2. Okay, so what is the domain restriction here? Well, we know square rooting requires what? It requires the inside of the square root to be greater than or equal to 0, right? It could equal 0, unlike the log, but it has to be greater than or equal to 0. Once we get negative, we get imaginary numbers, and so we don't want that right now. Okay? So, and it's also important to point out that if the root is even, so if this is, we know this is 2, right? Because it's an implicit 2, it's invisible. If it's 4, 6, 8, any even number, it has to be greater than or equal to 0. So let's just solve for x. So x has to be greater than or equal to 3. That's the only constraint on g of x's domain. So this again is how you can write it in inequality notation. In set notation, we just write g of x, the domain, we include 3, and we go to positive infinity. Okay, so that's the domain, and we looked at this algebraically, right? We found the domain algebraically. We didn't even consider the graphs, and I did that on purpose because now we are going to look at the graph. Okay, so here we have f of x is log 3 minus x, and g of x is square root of x minus 3 minus 2. And we want to graph these. We want to say h of x is equal to f of x, right? That's f of x. And in the values for x is less than 3. And that's perfect because that's the domain of f of x. Okay, it's equal to g of x for x is greater than or equal to 3, and that's kind of perfect too because that's the domain for g of x. So we can do one of two things. We can graph it using our calculator like it says, or we can use transformations from the parent graph. So let's use transformations from the parent graph. So the parent graph of f of x, let's call it y sub f, is equal to log of x, right? And we know log of x has a vertical asymptote here on the y-axis. It crosses the point at 1, 0, and then it goes up, and it goes down to the left, all the way to infinity and beyond. Okay? So this is log of x, and we know that the input now is going to do what? To get our f of x, we need to go from x to 3 minus x. Okay, so this gets a little complicated, so make sure you pay attention because 3 minus x is the same as negative x plus 3, right? And that's the same as negative 1x minus 3. Okay, because if you factor out a negative 1, you're left with that. And why am I doing that? Because I want to make sure that we see, because it's a negative x, we're going to reflect across our y-axis, right? And because it's negative 3, we want to shift horizontally, so horizontal shift to the right. So because it's a negative x and a positive 3, we need to factor out the negative 1 to see x is minus 3, because that minus means shift to the right, whereas a plus is shift to the left. So it's a little confusing. So then we can go ahead and reflect it. So let's do it in 2 stages. We're going to reflect it across the y-axis first. So this is the reflection across the y-axis. And then we're going to shift it to the right by 3. So starting here, 1 to the right, 2 to the right, 3 to the right. Okay, so that point moves to here, which is 1, 2, 0. And at 3, 0, now is our vertical asymptote. It goes down and up. So here in yellow is f of x. And it is f of x, right, in yellow. Okay, so now g of x. Let's use the parent function y sub g is equal to square root of x. We know square root of x starts here at 0, 0 and goes up to the right. Okay. Now we want to do minus 3, so minus 3 means we want to shift to the right. So we want to go the input from x to x minus 3, so that's shift right by 3. We could say horizontal shift to the right by 3, right? And then we want to look at the minus 2. So minus 2 is going to be vertical or shift down by 2. Vertical shift down by 2 units. Okay. So I'm just going to do this in one quick step. So we're going to go to the right by 3. So starting here, 1, 2, 3 to the right, and 2 down. 1, 2 down. Okay? So this is now g of x. So let's put this on the same axis. Okay. So the important point is 1, 2, 3, because we know for x is less than 3, so to the left of this line, we want to look at the graph here in yellow, which is our log function. So it has, let's use yellow. So it goes to this point, it goes down, 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 down forever, and then up, up, oops, connects, up, 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 right? And then starting here at, let me put it back in blue, -2, right? -2, now I'm copying this part for x is greater than or equal to 3, has a point right here, and then it goes up to the right, right? Okay, so this is our function h of x. So this is h of x. Okay, so we graphed that. You could have used your graphing calculator. I just wanted to show that we can do this without a graphing calculator. And now we're on part, so that's part B. And part C is it says, why is h of x not continuous at x equals to 3? Okay. So, why is it not continuous? Why is h of x not continuous at x equals to 3? Oops. So why isn't it continuous? Well, what do we see here? Continuous. If you guys remember, continuous means that if we're going on our graph, okay, so if I'm writing my graph, I'm falling, down, and I go down, and then at x equals 3, I jump back up to here, right? So we're going from -2 at x equals 3 to, if we go one little bit to the left, we're at like -infinity down here, right? So that's like a big infinite distance between those 2 points. So why isn't it continuous? Well, we can explain it as there is an infinite jump, right? Because it goes from -infinity and it jumps up to y is equal to -2. An infinite jump to the left of x equals 3 to x equals to 3. And how can we say that? Well, we know the limit as x approaches 3 from the left, right? So if we're writing this from the left, is equal to -infinity, where we know the limit as x approaches 3 from the right, it's equal to -2. And this is of h of x, right? The limit of our function h of x. Okay, so all of these are showing why it is not continuous at x is equal to 3. So right here is x equal to 3. Okay, finally D. D says, what is the range? So I'm going to just do this right here. Looking at the graph, D, what is the range? Well, we know that there are points all the way from -infinity, right, on this left side of 3, to all the way at positive infinity. So the range of each function. So we have to do that. We have to do the range for each function. So what are our functions' names? They are f, g, and h. So f of x, the range goes from where? From -infinity, so this is the left side, to positive infinity. -infinity to positive infinity. G of x, the range starts at, so we're looking from bottom to top, so it starts at -2, and it includes -2, and it goes up to positive infinity. And h of x, the range basically is like you OR all these, so it includes any part of the range, so it's going to be from -infinity to positive infinity. So this concludes CPM Calculus Chapter 2, number 50.